Hi, welcome to this promotional video on our paper, Fully Convolutional Networks for Time Series Classification. I am Ehtashamul Haque and I'll guide you through this presentation. At first, let's talk about the gap that we were trying to address. We wanted to create a quantum convolution layer that has all the functionalities of its classical counterpart. Compared to classical convolution, existing convolutional layers lacked modularity. They were not freely scalable, they couldn't handle arbitrary channeled inputs. Worst of all, most of the implementations were not learnable. Additionally, the 1D variant of quantum convolution is very poorly studied. As such, in this work, we have proposed a new convolution algorithm, Quanv1D, which overcomes all the previous shortcomings and works on par with classical convolution. Now, if we look at how Quanv1D processes the data, we can see that it works exactly like classical convolution. The main difference is that instead of regular filters, we are using learnable quantum circuits as kernels. Additional details and nuances of Quanv1D can be found in our paper. Now, to test the efficacy of our new layer, we built a new model called the Fully Convolutional Network, or FQN in short, where all the learnable layers are Quanv1D. It is to be noted that the term fully does not imply a fully quantum model. FQN is in fact a hybrid implementation as we had to use batch normalization layers and ReLU activation functions which do not have any quantum counterparts. To test the model, we benchmarked it on 20 datasets from the UCR and UCI time series repositories. After compiling the results, we found FQN to actually outperform its exact classical counterpart, FCN, owing to its self-regulation property. For completeness of the comparative analysis, we also included the two existing 1D convolutional models and some state-of-the-art TCNs during the test. On average, we found FQN to surpass all other models by some margin in terms of classification accuracy.